Okay, we're going to solve the system of equations. We want to find numbers for x, y, and z such that they satisfy these three equations. I'm going to start off by writing down the coefficients and the force vector in a matrix, augmented matrix. And I just pick up 3, 1, 1, negative 1, 0. These are the coefficients of the variables x, y, and z. And then I put a vertical line which corresponds to the equals. And then I start in with that. I'm going to use elementary row operations. What I want is, I want on the first row on the far left, I want that to be a 1. I could divide by 3 to get to that 1, but I don't really want to do that because I do not want to have, I don't want to have fractions. So I'm going to swap rows 1 and 2. And I'll pick a different color just to highlight that a little bit. When I swap rows 1 and 2, this is what I get. The thing is, I need to be really careful not to make a mistake on that. Just the thing is, one little mistake just ruins the whole thing. So I'm just swapping those two. Row 3 stays exactly the same. Okay, so I'm just taking one more look at that. Then what I have is, as we see, is in the top left, on the first row, that's a 1. That's our start. And what we want is we want to have zeros below that. So we want below the 1, we want 3. Or we have 3, but we want it to be 1. So what I'm going to do is multiply row 1 by negative 3 and add it to row 2. Put that in the row 2 position. So I'll just copy down exactly the row 1 and also row 3. Those will stay the same. And then I'll go in and change row 2. So 1 times negative 3 makes 0. That's what we wanted. 1 times negative 3 plus 1 is negative 4. Then I get 4 here and 9. No, I think I got the last one wrong. 7. Actually, I think I got the other one wrong too. Okay, negative 1 times negative 3 is 3, and I'll add that there. Okay, now what I want is I want this 1 to be 0. So I'm going to take negative row 1 and add it to row 3 and put it in the row 3 position. Okay, so I'm keeping everything the same, but then I'm going to change the last row. So I add the opposite of row 1. And then now I'm focusing on the second row. The first row, I got exactly the way I wanted. I got the first column, and the first row. On the first row, the very far left number is a 1, and then below that is 0. And now I go to the second row, and what I want is that first non-zero number is to the right of the number 1, which is called the lead coefficient or lead entry. So that lead entry above on the far left is to the left of the negative 4, but I want that to be 1. And so the way I'm going to do that is I'm going to swap rows 2 and 3. Okay, and so let's see about that. Why would I do that? Because I want that on the second row, I want the first entry to be 1. I could divide by -4, but I don't want to do that because that will lead to fractions. So I have -1 there, but I want to go further and multiply row 2 by -1, and that will do the job to make that a +1. All right, now see, I have that as 1, that looks good, but I want below that to be a 0. So what I'm going to do is I'm going to multiply row 2 by 4 and add it to row 3 and put that in the row 3 position. So I have 0. So I'm multiplying by +4 and adding, and I get 0. +4 and adding, that's -12 plus 3 is -9. +4 times -4 is -16 plus 9 plus 7 is -9. So I'm moving ahead here. And so what I see is that on the second row, the first non-zero entry is a 1, and it's to the right of the entry, the lead entry above. And I have 0 below that lead entry on the second row. Now I go to the third row, and I want this -9 to be a 1. So this time I'm going to just go ahead and divide by -9. Okay, so it's going to try to do another color. So I have 0, 0, 1, 1. All right, this matrix is in reduced row echelon, or is in row echelon form. Okay, what does that look like? If you go to the first row, the first entry, it's called the lead entry, is a 1. It is on the far, that lead entry has zeros below it, and it is the far left. It's in the far left non-zero column. Then you go below that, and the first entry is a 1, and above it to the left is a lead entry. Below it, there are no lead entries. There's zeros below, and you keep going to the third row. The first entry is 1. So that's in row echelon form. What it looks like is an upper triangular matrix with zeros below the main diagonal. Once you get to that point, we can write the system. So this corresponds to the system x plus y minus z equals -1, y minus 3z equals -4, z equals 1. And as we see right off, we have the z coordinate. What we're going to do is we're going to back solve which means that we go to the equation right above z equals 1, which is y minus 3z. So the point being is there's no x there. And then we replace z by 1, and that results with y equals negative 1. So we got that coordinate. And then we continue, and we'll back solve again. And I'm going to write then the equation x plus y minus z equals 1. And then we go ahead and we replace y by negative 1. Z we replace by 1. And then so that's equal to 1. And so x minus 2 is equal to 1. Unfortunately, there's a mistake here. It's these small things. It's not even, it's careless of me, but when I copy that down, it's x plus y minus z equals negative 1. I put positive 1, and just because of that, I almost got the wrong answer, which is, frustrating after doing that. And it can be really hard, actually, difficult to find the mistake once you make a mistake like that. So then we get x equals 1. Okay. So now what I'm going to do is I'm going to check that this is correct. And what do we do when we check is we go back to the original equation, which is way up here, and I'm going to put in the places of x, y, and z blank spaces, and in those blank spaces I'm going to insert those coordinates that we found. Okay, so then I'm going to insert the coordinates we found, try to pick a fun color here. 1 is for x, for y is negative 1, and for z is 1. And so we see that 3 minus negative 1 is 4, 1 minus 1 minus 1 is negative 1, 1 plus 2 is 3. So that worked, that's always satisfying. So the solution is the point x equals 1, y equals negative 1, z equals 1. And that's all.